This is lesson 5.5 on augmented matrices. So this lesson represents a bit of a change in this unit. So up to this point we've talked about systems of equations and systems of inequalities. 5.5 on, we're going to be working with these kind of new mathematical objects called matrices. A matrix is a two-dimensional array of numbers, or a two-dimensional collection of numbers. Basically, think of your ordered pairs, ordered triples, so on, that we've talked about so far. Think of those as one-dimensional things. We just have a straight line of numbers. Now think of it as a rectangular collection of numbers. That's what a matrix is, some rectangular collection of numbers. Now most of the matrices that we run into are going to be the numbers are just going to be nice integers, but they can be real numbers, they can be complex numbers, they can be anything whatsoever. We will primarily work with integers, but they can be absolutely any number whatsoever. So here's a quick collection of just three different matrices. This first example we would call a 2 by 2 matrix. We're going to be working with them quite a bit actually. The bigger matrix in the middle is a 4 by 3 matrix. That's perhaps a little bigger than what we'll be seeing most of the time in this unit, but matrices do get that big. They get even bigger, in fact. And then finally, our last example, that would be a 1 by 4 matrix. Now we might worry, why are we dealing with this? Aren't matrices two-dimensional things? Well, yes, but sometimes we have a dimension of length 1, which is the case here. So even though we could probably just as easily represent this collection as an ordered quadruple, we can still consider it to be a matrix. Now the specific type of matrices that we're going to be talking about in this section are called augmented matrices. Technically, an augmented matrix could refer to a number of different things. It's any matrix where we tack on one or more extra columns at the end. For this section, we mean something very specific. The augmented matrices we are going to work with are going to be matrix representations of systems of linear equations. So we're going to look at how, if we're given a system of linear equations, we can rewrite that as a matrix. Now that might be beneficial for a number of different reasons. Matrices have a few different properties that we can work with a little bit more easily. Computers and calculators will handle matrices much more easily than it could a system of equations. So we will actually look at how we can solve a system of equations using matrices rather than our techniques of elimination and substitution. The technique is called Gaussian elimination, and in fact we're going to see it has a very similar flair to it as regular elimination that we saw a few sections back. But this time, instead of working with systems of equations, again, instead of working with equations, we'll be working with a matrix. So we'll run through a couple of quick examples of how to convert a system of equations into an augmented matrix, and then look at how to solve a system of equations using Gaussian elimination. All right, so let's consider this example. So the drill problems from this section are going to be extremely easy. The way that we convert a system of equations into an augmented matrix is we're going to take each equation, and that's going to correspond to each row in our matrix. So what we're going to do is we're going to write our matrix. Our first row, we're just going to put the numbers that we see. So we're going to put a 2 here, a 3 here, and a -6. For the second row, we're going to put the numbers that we see here. So -4, 9, and 2. That's our augmented matrix. Now sometimes, you'll see that sometimes we like to put a little bar here. That's just to indicate that this is, once again, an augmented matrix. This is kind of our base matrix, and this is the column that we've added on to it. Not a big deal here, but you will frequently see that done. So that's it. That's all we do here for this problem. Take our system of equations, rewrite it as this matrix, and that's it. For the drill problems, it's as simple as that. So we'll see one more example of this real quick, and then we'll move on to our application problem. The application problem, unfortunately, is a bit more difficult and lengthier, but we'll worry about that when we get there. All right, one more real quick. So once again, we're going to take each equation, and that's going to correspond to a row in our matrix. So this first equation will be the first row in our matrix. So we put a -5 here, minus 6y, so negative 6 here, and then a 10. I'm going to go ahead and put my little bar here to divide, to indicate the division between the variables and the constants. For the second equation and second row of my matrix, 5x, so put a 5 here. Y, remember, if there's not a number there, it's an implied 1, equals 0. That's it. So once again, the drill problem's super quick and easy. The application problem that we'll take a look at here in just a moment takes a little more time. Alright, so here we're asked to use Gaussian elimination to solve the system of equations. So the first thing we're going to do is we're going to rewrite the system as a matrix. So my first row in my matrix is going to correspond to my first equation. Second row will correspond to my second equation. And then my third row corresponds to my third equation. So there we go. So I'll go ahead and put in my separating line there. When we use Gaussian elimination, we are allowed to do one of three things. We can either interchange two rows, so I could make my first row my third row and vice versa. I can multiply a row by a number, or I can add two rows together. Now sometimes we'll group things together and do a few of those simultaneously. Using those techniques and only those techniques, multiplying by number, adding them together, or interchanging rows, what we want to do is we want to get this into row echelon form. That's a fancy phrase. All that means is we want to get ones along this diagonal here, and all these numbers underneath it we want to be just zeros. The way we're going to do that is proceed column by column. Let's get column 1 exactly the way we need it to be, and then column 2, and then column 3. So the general rule of thumb is get your 1 in place first, and then take care of the zeros below that 1. So notice we already have a 1 where we want it in our first column. We want a 1 here, a 1 here, and a 1 here. So we already have the 1 where we want it to be. So we want this 3 and this 2 to become zeros. The way we're going to do that is we're going to add a multiple of row 1 to row 2 and to row 3. So notice, if we multiply row 1 by negative 3, so let me write here negative 3 R1, and we add it to row 2. If that is my new row 2 value, that will get rid of the 3. That will make this a 0. Similarly, if I multiply row 1 by negative 2 and add that to row 3, that will give me my new row 3. So negative 2 times row 1 plus row 3 equals my new row 3. So notice here the only rows that actually change are row 2 and row 3. So row 1 I'm just going to go ahead and rewrite the way it is. I'm going to multiply it by number and add it to one of my other rows. But I'm going to rewrite those in row 2 and row 3. Row 1 stays exactly the same. So I multiply everything in row 1 by negative 3 and add it to row 2. So negative 3 times 1, that's negative 3, plus 3, that's going to be 0. Multiplying by negative 3, I get negative 9, plus negative 1, that's negative 10. Negative 3, multiplying by negative 3, that gives me 3 plus 2 gives me 5. And then multiplying by negative 3 gives me positive 9, plus 1 gives me 10. Similarly with row 3, I multiply my original row 1 by negative 2 and add it to my original row 3. So negative 2 plus 2 is 0. Negative 6 plus negative 1 will be negative 7. Positive 2 plus 1, that will be 3. And positive 6 plus negative 1, that will be positive 5. So notice my first column is exactly the way I want it. I have a 1 here and zeros beneath it. All right, now I move on to my second column. I want 1s along the diagonal, so I want to have a 1 right here. The way I'm going to do that is I'm going to multiply this whole row by negative 1/10. So negative 1/10 times row 2, that's going to give me my new row 2. So I'm only changing row 2, so row 1 and row 3 will be exactly the same. So 1, 3, negative 1, negative 3, 0, negative 1/10 times negative 10 will be positive 1. That's the whole reason we chose negative 1/10. 5 times negative 1/10, that will be negative 1/2. And 10 times negative 1/10 will be negative 1. And once again, row 3 is exactly the same. Nothing changes. Okay, so I now have my 1 where I want it to be in my second column. So I want to get everything below that 1 to be a 0 now. So the way I'm going to get that to be a 0 is I'm going to multiply row 2 by 7 and add it to row 3. Notice that that will make this 0. 7 plus negative 7 will be 0. So my new matrix, once again, the only thing that I actually change is row 3. So row 1 is the same. Row 2 is the same. I do multiply row 2 by 7, but I add it to row 3. So row 2 itself does not change. Now I add row 2 times 7 to row 3. So 0 plus 0 will be 0. 7 plus negative 7 will be 0. Negative 7 halves plus 3, so it's going to be 6 halves. So that will be negative 1/2. Then negative 7 plus 5, that will be negative 2. Okay, so I now have my second column the way I want it to be. I have a 1 right here and a 0 down below. Once again, our goal is we want 1s along the diagonal and 0s below it. So I had my 1 in column 2, and I got the 0 below it. The last thing I need here is to make this a 1. So I'm going to do that by multiplying row 3 by negative 2. So negative 2 times row 3, it's going to give me my new row 3. So row 1 stays the same. Row 2 stays the same. Row 3, I multiply everything by negative 2, so 0 here, 0 here. This becomes positive 1. This becomes positive 4. So this is in what we call row echelon form now. There's also something called reduced row echelon form. What that means is we have 1s along the diagonal, 0s below it, and 0s above it. You can do that at this point now by using the same technique of adding multiples of one row to another to get 0s above this diagonal now. But there's really no reason to worry about that. What we're going to do instead is at this point, we're going to rewrite our matrix as a system of equations. So my first matrix is the equation x plus 3y minus z equals negative 3. My second line is y minus 1/2 z equals negative 1. And my last row is simply z equals 4. So since I know what z is, I can plug it into my second equation to solve for y. So y minus 1/2 of 4, that's going to be negative 1. So that's going to be y minus 2 equals negative 1. So y equals positive 1. All right, now to get x, I'm just going to plug in x and y into the first equation. X plus 3 times 1 minus z, I know is 4, equals negative 3. So let's see here. 3 minus 4, that's going to be negative 1. So if I add 1 to both sides, I get x equals negative 2. So my final answer then is negative 2, comma 1, comma 4. So this really isn't that much more or less work than if we just did regular old elimination. In all honesty, it might be a little bit more work doing this all by hand. One of the benefits of handling systems of equations in matrix form is that calculators and computers can work with them a little bit more easily. So it's good to know how to do these by hand, just so that we understand the technique that our calculators are using. But from a practical point of view, these more complicated systems of equations, most likely, if you need to solve them for your job or whatever, pretty good chance you'll want to convert it into a matrix and then feed it to a computer to let it crunch the numbers. But this is essentially what it's doing behind the scenes.